Okay, so today we are going to start the new session on system on chip verification and debugging, right? Already the demo session have completed what we are going to cover in this 3-month course. Okay, for each week, what are the things we are going to cover? And so today is the first session. So we'll see what are the things we are going to cover in the session 1. Okay, so these are the content of the session today. So the detailed explanation of SOC architecture. Okay, not for today, for this week. So for today, we are going to cover the difference between ASIC and FPGA, the brief explanation about ASIC. Okay, in ASIC, we have different kinds, right? Classification. So that classification and what is meant by FPGA. So uh, where we use the FPGA and applications and SOC architecture. What is the difference between SOC and NOC? And what are the different blocks available in the SOC architecture, and what is the difference between monolithic and multi-chiplet. Okay, if you see the SOCs, whatever the history, if you see, different companies have their own SOCs. Okay, so Intel company have the x86 microprocessor, and AMD, the ARM have some RISC-V processor, type processor. So each company have their own SOCs, right, with a different processors, a different number of cores. So we'll see commonly what is meant by monolithic and multi-chiplet SOCs. Okay, so these are the things we are going to see today. Okay, so if you are facing any doubts anywhere, okay, so please let me know, okay, so that we can discuss our doubts clearly, and you can solve your doubts here only in the session itself. Okay, so first we will start with ASIC versus FPGA. So can you tell me what is mean by ASIC? Can anyone tell me what
Application
is?
specific, yeah. Application specific integrated circuit.
Okay.
It's acronym for it. Yeah.
Okay, so application specific integrated circuit, it is just a acronym for that. But if you go in depth of ASIC, there are so many things to know. Okay, so we'll see just brief on ASIC. Okay, so ASIC is nothing but application specific integrated circuit. Okay, it is mainly used for non non-standard integrated circuits. Okay, so if you see, as the name suggests, it is only for specific operation. Okay, so it is a permanent chip and used for the specific operation. Okay, there are different types of the ASIC chips. Okay, in the modern days, we are seeing 32-bit processors, memory blocks, and the large building blocks. All these things will be included on the ASIC chip. Okay, so overall design can be made into a single integrated circuit, and the number of additional circuits will be reduced. We can reduce the number of additional circuits. Okay, so ASIC designs mainly some of the modern chips called as SOC, right? So ASICs also known as SOCs. Okay, like modern ASIC, but not uh, here different types of ASICs are there, right? Full custom, semi-custom, programmable, but these are not related to the SOC. Okay, so we'll see the type of ASIC, and ASICs are mainly, we already know how the ASIC chips will be designed, the design flow, VLSI design flow, like there will be front-end design and the back-end physical design. The various steps will be involved, right, for manufacturing. So by using the hardware description language using the Verilog or VHDL, we will describe the main function of the ASIC chip. Okay, so coming to the types of the ASIC, there are basically 3 types of ASIC chip designs. Okay, one is a full custom design, semi-custom design, and programmable ASIC. Okay, so what is meant by full custom design? Did you have any idea? Can anyone tell what is meant by full custom design? This is just introduction, okay? Before going to SOC, we need to know about history, the things, right? How SOC emerged and different SOCs, how we have taken. So that's why just the introduction. Okay, so full custom design is nothing but it is also a integrated circuit which consists of different types of blocks, different type of components like resistors, transistors, okay, digital logic, uh, like a digital logic in a sense, every block, okay, every component like a gates or registers or flip-flops, whatever, and the capacitors, analog circuits, these all are partitioned in a circuit layout. That is nothing but full custom. Okay, so mainly microprocessor is nothing but a simple example for the full custom integrated circuit. Okay, so usually to manufacture this, it will be very expensive and it will take some more time because we will do the manufacture as we will manufacture full custom design in the handcrafted manner, like manually. There are no equipment like the tools, okay, from the computer, okay, from advanced tools. We are not manufacturing like that. Okay, it is just like a handcrafted, so it will take time and maximum performance and minimized area. Okay, not compared to the SOCs and all, but full custom also provide the maximum performance. Okay, so next one is the semi-custom design. Semi-custom design is also one of the alternate to the full custom design. Okay, so here we can use the components from the standard library. Okay, as the name, if you see semi-custom, that means from the library, we are taking the components and we are customizing those components. With the components, it is a pre-designed. Okay, so some mask layers will be there so that all pre-designed or logic cells we will customize according to the design. Okay, so what is the main advantage of using predefined logic cells from the library? Means it can make the semi-custom ASIC design easier. Okay, so we can reduce the time. Okay, if you see the difference between system verilog to UVM, system verilog means we need to develop everything from the scratch. Okay, if you want to develop a test plan or any test bench, we need to develop everything from the scratch. We need to create the generator, we need to create the driver, we need to create monitor, everything. There are no predefined libraries. Okay, but if you see UVM, all are predefined library. Okay, no need to develop anything from the scratch. We can use the library and we can utilize the libraries and we can create according to our functionality. Okay, same as okay system verilog and UVM. So, and semi-custom design also have some other two types. One is a standard cell based ASIC and gate array based ASIC. Okay, so we'll see what is meant by standard cell and gate array. So standard cell is nothing but it is also a predefined, which is classified from the semi-custom, right? So it will have different type of logic gates, flip-flops, multiplexers, demultiplexers, all. So these predefined cells are known as the standard cells. Okay, so flexible blocks, there will be flexible blocks. If you see the block diagram here, standard cell area, fixed blocks with a size. Okay, so the standard cell area can be usually larger standards only. Okay, because at the time we have used in terms of micrometers, right? Nowadays we are using nanometer, but in terms of standard cell we have used the micrometer. Okay, so the larger standard cells also we can call as mega cells. Okay, so full custom blocks or like fixed blocks, okay, mega functions or system level macros, we can call like this. So whatever, if you see here, the standard cell area and how we have taken the fixed blocks, okay, all these are connected in a right side. If you see the stick diagram manner, okay, so the blocks will be converted into the transistor level. So placement and providing interconnections of cell is also a major thing in the ASIC design role. So these are standard cell based. Okay, just taking some of the blocks and interconnecting each other. Okay, and what are the main advantages of standard cell based means we can save some money and we can reduce the time also. So less risk compared to the full custom device. Okay, and and another we can also see some disadvantages here. What are the disadvantages? Here we require the libraries, right? So by using the libraries we are doing customization. So for preparing the libraries and all, for standard libraries it will some expensive. Okay, so in terms of that it will be expensive to fabricate these designs. Otherwise we have the advantages with the standard cell based ASIC design. Okay, so it was mainly most of the companies like in past, like in 30-40 years back, like companies like LSI Logic or some uh, Harris Semiconductor, like these companies use these standard cell based ASIC. Okay, so these are the what is meant by standard cell. Have you understood, everyone? Mostly micrometers. Okay, here the technology, CMOS technology we have used in terms of micrometer, like 1.5 micrometer, 0.6 micrometer, in the range voltages, in the range 25 volts, 10 volts, in that range. Okay, so what is the gate count? If you see a micrometer in terms of micrometer CMOS, what will be the gate count and die size? So gate count will be around 10,000 or 60, 10 to 60, or minimum 1 lakh. Okay, below 1 lakh only. Okay, so that will be the gate count in the standard cell based ASIC design. Next one is gate array ASIC design. So what is a gate array? Gate array is also a prefabricated silicon chip. Here also we will have the predefined silicon, predefined blocks like transistors, everything, logic gates. Okay, so here the gate array we can also call as a base array. Why? Because here we will use the base cells. Okay, so whatever, if you see here right side, the element, okay, we can call it as a logic cell or element. Okay, which is present in the base, that is nothing but base cell. Okay, so usually gate array is on based on the masked gate arrays. Okay, so mainly it have the predefined logic cells from the gate array libraries. Okay, there will be libraries in the gate array for better design. Okay, for better and easy design. So that what are the advantages? We can reduce the time and cost will be low. Okay, so advantages, these are the advantages compared to the full custom design. Have you all understood, everyone? Again, in this gate array also we have three types of gate, because gate in the sense channel matter, right? So we can use without channel, there is a channel gate, channel less gate. Okay, structure gate array, like this. Okay, if you want brief on gate array, you can just go through those, how the channel is, how the channel. Okay, because our course is not intended to that, right? So this is what the gate array based ASIC. Have you all understood? Most of the companies like Harris Semiconductor, that time, very in history. So Texas Instrument, Texas Instrument is also one of the company which manufactures the gate array based ASIC. Okay, so mostly at one micrometer. Okay, 2 micrometers, up to this size we have used. Okay, up to 2 lakh gate count. Okay, everyone clear?
So there will be a trade-off between the product life cycle and this performance of product if we are using gate array or standard cell based basic. Like in standard cell basic, performance can be better, but long product cycle or gate array is a short product life cycle. Is it true?
Yes.
Okay.
Yeah. Okay. So that is what the difference. And next, programmable ASIC. So what is meant by programmable? In ASICs, we have standard cell, semi-custom, full custom, and programmable. So what is meant by programmable?
We can write our own logic.
Okay. Okay, so programmable logic devices. Programmable logic device is nothing but where we can program to obtain some logic device. Okay, so programmable is nothing but reprogram. We can do reprogram. Okay, the main advantage of reprogrammability is we can replace the special purpose logic devices like whatever logic gates, flip-flops, counters, multiplexers, whatever, any semi-custom applications we can replace. Okay, so that what happens, it reduces the time for next application. If you want to make any next application, we can reuse the chip. No need to waste the chip for single application. We can do many applications in single chip. So it reduces the design time and it reduces the cost. Mainly it reduces the cost and easy to reach to the market. Okay, so it mainly programmable logic device means it mainly depends on the gates. Okay, so it mainly consists of arrays of gates like AND gate and the OR gate. Okay, so in that gates we can be programmized to the logical function, whatever the logic function we have required, we will realize that required logic into that gates. Okay, so mainly in this we have different programmable logic devices. These are mainly why PLDs are very essential means there is no inexpensive. These are very cheap cost. Okay, in terms of software tools. Okay, very cheap, inexpensive, and we can develop very quickly. Simulation or testing using software tools is very quickly. Okay, and design cost is comparatively low, as we said. So these are the main advantages. Okay, and what are the different classification? Programmable read only memory. Okay, next one is programmable array logic, programmable logic array. Only small differences are there between these. Okay, so how we will connect the fixed memory and how we will connect the programmable memory. Okay, if you see, programmable read-only memory means it is nothing but one memory chip. Okay, so where we can write the data only once. We can write the data only once. Once data is written on PROM, it remains forever. Okay, so that is called one-time programmable memory. Okay, so here uh, there are so many applications like in computer BIOS we use the programmable PROM, and there also reprogramming is not required in the computer BIOS. Like that, here we have the fixed and array, gate array. Okay, so I didn't mention here. Okay, so you can go through the differences between programmable read-only memory and array logic and logic array. So next one is a generic array logic. So what is meant by generic array logic? Generic array logic is also one type of PAL, okay, programmable array logic. Okay, so it have some matrix and programmable output cells. Okay, so suppose if you see the diagram, generic array logic, it have some CMOS. We mostly use the CMOS material as a semiconductor, right? So CMOS programmable and array, and it is connected to the output, the devices, and output here and input this side. Okay, so here GAL is mainly improved from the PAL, so programmable array logic. So anyone know what is meant by programmable array logic? There will be one programmable AND array, and the programmable AND array is given the output of the given to the fixed OR array. So here we'll get the outputs. So how we will what is the intention of these two? Whereas AND array is programmable and fixed array is not programmable. Okay. Have you understood, everyone?
Yes, ma'am.
Okay, so from this we have from this generic array logic has came, and next one is the complex programmable logic design, CPLD. CPLD is also defined. It is also came from the network of PLDs. Okay, which that are connected in the switching matrix manner. Okay, so what is the how we can write the CPLD general block diagram? So there will be one interconnect matrix will be there. Through this matrix, we are connecting different blocks. Okay, this is one digital block, or there is some other digital blocks, whatever. And here some other digital blocks. All these digital blocks we are connecting to the interconnect matrix, and here there will be one IO device. Okay, here IO device, through the IO device we are connecting here, and this will be the connections with the IO device. Okay, so this is the CPLD, complex programmable logic device. Okay, so all these are connected in the matrix manner, which are reconfigurable whenever you change the connections between all functional blocks. Okay, depending upon our requirement, we can change the blocks. Okay, so each functional block, so this is one functional block, this is another functional block. So each functional block contains a reprogrammable and or array. Okay, along with the macro cells. Okay, here there will be one and or. So wherever PAL has. Okay, so through these and or blocks we will connect. Anyway, if you convert any digital block, we will get the and or, right? If you convert into and or into universal gates, then it will be NAND NOR. Okay, basically and or at the time of ASIC designs. Okay, so every functional block have the end array and or array along with the macro cells. Okay, so there will be multiple types of logical functions, whatever, maybe it is a combinational logic circuit or sequential logic circuit. Multiple logic functions will be implemented with the CPLD. Okay, so it is connected with the external, these are the external IO blocks. Okay, so we will connect with some external IO blocks which is coming from the different blocks. So the entire device consists of how many number of gates? nearly thousands of gates. Okay, so therefore, for complex designs, other than PLD design, CPLDs will be implemented. What is the PLD? PLD means only this separate block. This separate block is the PLD. But multiples of PLDs, like in the multiple functional blocks, there will be multiple end array, end or arrays, right? So for the implementation of complex design, we are going to the CPLD. Okay. From the CPLD, field programmable gate array has introduced. Okay. So what is meant by field programmable gate array? Present in the modern IC verification, present days we are using the FPGAs also. Mostly we are using SOC, but while connecting with the SOC in the computer system, in the motherboards, a few FPGAs also using, right, nowadays also. So here also we'll use HDL language for circuit design and synthesized into the FPGA core. Okay, so it can be used to realize the simple digital logic gates to the complex mathematical equations. We can build simple logic designs and complex also, right? So mainly what is meant by FPGA? How the structure of FPGA? This is the CPLD. Before whatever we have seen, that one is the CPLD. But in FPGA, there will be complex logic blocks and switches mostly. Suppose here there is a one logic block and second logic block and third logic block. Here there will be switches interconnection. And here there will be a switches interconnection. How we'll connect each logic block. So here the switches will be connected like this. So here some of the switches will be there. Through the switches will connect all, or we can also tell as interconnect blocks. Okay, these switches we can tell as a interconnections. Now how we are using interconnections in the SOC level? AXI interconnects, AHV interconnects, like that we are using. But in the FPGAs, we'll use the switches as the interconnects. Okay, so how we will make the connection between this logic block to this logic block? We need to make the connection through the switches and the interconnects. So these are the interconnects and the switches, right? So if I want to make the connection between one logic block to another logic block from here to here, first I need to send to this interconnect and the nearby switch, maybe upside or this. Okay, nearby switch to this switch and then this bus path, so that here I can connect with the next logic block. Okay, so here what is happening? The complex designs are divided into small functions. Okay, so logic blocks are used to implement these small functions. Okay, so and we can make the connections using the programmable interconnects. This is what the architecture of the programmed FPGA. Okay, these are the sub functions which we can implement using each logic block. Okay, so that all the interconnections can be programmed using the switch boxes. Okay, did you all understood, everyone? I'm telling this is one logic block, right? So this is one logic block, second logic block, and third logic block. So what will be there in the logic blocks? What will be there in the logic blocks? Are you understanding what I am telling? Hello.
Yes.
Can anyone explain what I have explained with this diagram?
So in the logic blocks, we can have some predefined databases based on the programming we have done on the FPGA, and like memories can be what we call it as a lookup table, which is basically a combination of AND or NOT gates, and we have some definite inputs and outputs of this data, what based on the programming we have done in the FPGA. So this is how this processing takes place.
Okay. Okay. So logic blocks are nothing but it will implement the sub functions as we discussed. Those logic functions are nothing but it may be both the combinational logic circuit or sequential logic circuit. It will implement both logics, right? So in mainly here in the logic block, it consists of the lookup table, as he said. It consists of one lookup table, one register, or we can also tell any flip-flops, and the multiplexer. Okay, so these are the main three blocks. What is the lookup table? Lookup table is mainly used to implement the combinational logic functions, right? So whatever inputs are getting here, okay, this lookup table will implement the functionality, and it will generate the output according to those inputs. Suppose this lookup table we have written for the full adder. Okay, so what are the inputs we are providing? A, B, C. Okay, that lookup table will be converted that A, B, C all combinations to the single output or two outputs. Okay, so that output we are giving to the flip-flop. So what is the flip-flop here? Mainly register, not flip-flop, register. For registers, which flip-flops we will use? D flip-flop, right? So the D flip-flop will store the data of lookup table. Okay, so this data will be stored in the D flip-flop, and output of D flip-flop is given to the multiplexer. So the multiplexer will select the output. Okay, so this is the simple block diagram where we use in the FPGA's block diagrams. So we classify in that way based on the different functionality, different blocks. Okay, everyone understood?
So here the lookup table is basically we call it as a memory. Or the basic building block of lookup table will be a D flip-flop, which stores 0 or 1 value, and the D flip-flop is eventually is made up of some gates only, and the combination of some gates. So this is how it is present in the FPGA or some else. So
See, mainly for lookup table, we will use the SRAM.
yes.
SRAM is nothing but a memory, right? So by using the SRAM, we will implement the lookup table so that whatever
Yes.
the function is there, it can be implemented by storing the data into the SRAM. Okay, so output from the lookup table is given to the both the input and the D flip-flop. So D flip-flop is used to delay the output. Okay, because
Okay.
for multiplexer, it should go in time, right? So depending upon the application and all, the multiplexer will select the lookup table output, and it will delay the output, basically the D flip-flop. So that whatever selection line input of the say by using the select input, the multiplexer have both it will use both the block diagram, whatever blocks, right? Digital blocks, so that such blocks will get interconnected, and finally using the switch, it will get the complex circuit, desired complex circuit, whatever.
This mux can be placed at the input and output both of the
Yes.
LUT.
No.
Okay,
The
so
multiplexer we can put at the output of the lookup table. So from that multiplexer, we are making the connection to the switches. Suppose here there is a multiplexer here making the connection to the switches.
So if you want to switch the input or input and output are fixed every time, or we how we manage the inputs of a particular LUT, like it is a fixed thing, then we are
Yes.
just only
Mm.
we are only selecting the output of the LUT.
Yes, yes. Based on here, not only one block, we have different logical blocks, right? Based on the functionality, which output will be selected. So those switches will be selected. Previously, we'll make the connections for that
So
before only.
and as you
Mm.
said, LUT is an SRAM. So SRAM is just a memory which have the different memory location, have different data stored, and this is just a implementation of our truth table of particular logic. Is it
Yes.
correct? Yeah.
Yes.
So
Yeah.
okay.
Okay. So can you please all join? So that is what the FPGA implementation part. Okay. So mainly compared to the whatever we have discussed, the logic devices like PL or PLA or GAL, CPLD. Okay, compared to all these devices, FPGA has very high advantages. Okay, more advantages, like it have high density. Okay, high density in the sense, in the single FPGA chip, we can integrate thousands of gates, millions of gates. Okay, nearly 10 million gates, 8 to 10 million gates we can integrate on a single chip. But what is the before count for PAL or PLA? What is the count? Just thousands of gates we can integrate using the PAL or these different logic devices. But using the FPGA, we can implement 8 million gates up to that. Okay, so that it is also more faster. Okay, compared to remaining all classification, FPGA is a more faster and more efficient with than other pipeline architecture, all these compared to all these. Okay, and it is also reprogrammable, which is one of the most advantage. So yeah, these are the advantages of FPGA. Everyone understood? So mostly where we prefer the FPGA applications. Where FPGAs are used mostly in the industries.
While validation, so that it will just
Okay.
mimic this chip that they want, and they will check the signals in it.
Okay. So while manufacturing the permanent chips are nothing but ASIC chips or SOCs. So while manufacturing these, there will be continuous changes will be there. We cannot tell that like at a time one time only we'll get the correct output and no need to make any changes. So it's wrong, right? So whenever we need continuous changes, okay, FPGA is the best solution because it is a reprogrammable. We can reprogram anytime. So it doesn't take much time. Okay, compared to the ASIC. ASIC means once we dump the program, we cannot change. So while we are making bulk, while we are manufacturing any integrated circuit in bulk, or if any integrated circuit coming to the market, before they will check with the FPGA only. Once everything fine in the FPGA, okay, then only they will give the allow to the ASIC, okay, to integrate into the ASIC chip. That is the FPGA. In FPGA, we also have the disadvantages. So what are the disadvantages in FPGA?
Fix a gate count.
Fixed gate count. Okay. Okay. So
What's
many
more?
FPGAs are slow and it consumes more power. Okay. And if you see configuration of FPGA, what is the configuration of FPGA? How it will store the data? Using RAM, right? RAM in the sense it is a volatile in nature. So once power off, the data will be lost, right? So once they lost the power, it configuration is lost, right? So that's why there is the disadvantage with the FPGA. So practical applications, whenever we are storing externally, so non-volatile flash memories are preferred. Okay, so from there data is automatically we can restore for retaining the power after retaining the power, right? So that's why FPGAs are mostly not considerable because of its volatile nature. Okay. Everyone understood? Okay. Next one is a field programmable gate array. So already I have explained this block diagram, right? How logic blocks and how interconnections and all. So next, what is a system on chip? So what is mean by system on chip? Everyone clear? If you don't, if you have any doubts, please let me know. We discuss. Okay. Do you have any doubts? If you have any doubts, please let me know so that we can discuss. Okay. So what is system on chip? So this is our course, right? Mainly. So we'll see the overall detailed explanation of system on chip. Okay, what is mean by SOC? What are the different variations in SOC? And the past history of SOC's versions and present SOC's monolithic and multi-chiplet. How we are integrating CCD and IOD. CCX configuration. What is the difference between CCD and IOD? All these things we discuss. Okay. So what is the SOC? So SOC is nothing but a system on chip. Am I audible, everyone? No one is answering.
Yes, ma'am, you are audible.
Okay. Okay, Aditya, tell me what is SOC?
SOC is nothing but a system on chip, which is a integration of all the IPs and the subsystems.
Okay. What is the difference between IP and SOC?
SOC contains both hardware and software components.
Okay. Okay. Any other answers? What is the responsibility of subsystem and IP? What are the different blocks involved in the SOC? What are the different interconnects involved in the SOC? What is meant by control input and data control unit and data unit in SOC? Okay, we'll discuss these things now. Okay, so SOC is nothing but is an integrated circuit which integrate all the components into a single chip. Okay, single chip means it will contain maybe both analog, digital signal, digital circuits, multi mixed signal, and digital signal. Okay, digital signal processing we have, right? So digital signal and some other frequency, radio frequency functions will be there, and all these lie on a single chip substrate. Okay, so whatever SOCs are there nowadays, those are common. Nowadays SOCs are very common, right? Because of its low power consumption, mostly used for embedded applications. Automobile embedded means everywhere, automobile industries or mobile phones, everything, everywhere we are using the SOC based. So those are very popular because of its a high speed, high performance and low power consumption. Okay, so what exactly internal SOC have? So SOCs consists of mainly control units, memory blocks, timing units, and remaining other peripherals. Okay, so what are control unit? What do we have in control unit? Please respond.
It may store the control signals which will be responsible for the actions of the blocks.
Okay, so control unit is nothing but mainly what are different digital signal processors, microprocessors, microcontrollers. All these are the control units. Okay, so memory blocks means you already know what are the different memories: RAM, ROM, EEPROM, EEPROM, and flash memory. These are the basic memory units inside the SOC. And timing units. What are the timing units? Like PLL, oscillators. Okay, these are the timing units on the system on chip. And other peripherals like SOCs, counter timers, real time timers, and reset generators, power on reset generators. All these are. And also analog interfaces, external interfaces, voltage regulators, and different power management unit. In power management also we have power gating, power management, different techniques, UPF techniques will be there. So that is also one different team. Okay, so that is also a low power verification team which involved in the SOC for high performance. Okay, so these are the different different things in the SOC. Okay. And next, system on chip example. So what is a system on chip? What it contains? This is just a small example. Tomorrow we'll discuss very clearly on the system on chip architecture, how exact industries use the system on chip architecture. All those things tomorrow we can discuss. Okay, this is the simple example for the system on chip. Okay, so how it look like? It have the JTAG. Okay, JTAG is used to interconnect between two different devices. Okay, an ARM processor. There we can use any x86 or ARM processor or AMD Ryzen processor. Okay, anything. And voltage regulator, and it consists of different peripheral bridges for peripheral interconnect. And here system controller, advanced system controller. It have timing blocks, PLL, oscillators, RC oscillator, and reset control, brownout detect, power on reset. So everything, every block, watchdog timer, real time timer. So everything we are going to discuss, okay, in the next session, okay. So, and what is meant by PIO, peripheral interface, input and output. So here memory controller. In memory controller also, in this course, we are going to discuss the direct memory access controller. Okay, so I am planning to provide the two SOCs. One is a RISC processor, another one is the direct memory access controller, and AXI peripheral, AXI interconnect. Okay, so flash memory and flash programmable memory controller and peripheral data controller. These are the different blocks. And here, if you see Ethernet, USART, SPI, these are related to the protocol interconnections, and CAN, USB device, PWM controller, timers, counters. Okay, this is not exact SOC architecture. In actual SOC architecture, it will consist of core. Okay, in the processor side, we have the core caches. Okay, CCD configuration or CCX configuration, number of core configuration, and IOD side, IO blocks. Okay, North Bridge IO or South Bridge IO or DFT or DFD or different PCIe, Ethernet, all these will be separate. Okay, so we'll discuss those things. And next one, what are the advantages of system on chip? What are the advantages? Mainly advantages are low power, low cost, high reliability, small form factor, high integration levels, fast operation, greater size, greater design, and small size. Okay, so these are the main advantages. I think no need to explain each, right? So we already know. And next, disadvantages are the fabrication cost, increased complexity, time to market demands. Okay, because while we are doing on the version, suppose SOC 10, while doing SOC 10, we need to prepare the plan for SOC 11. Okay, we know how fast the technology is improving in the market, how fast the mobiles are getting in the market. Okay, for every year, new version mobiles are getting, right? So when the actual manufacturing is happening, when actual all the things development, each block development. Okay, in SOC there will be several blocks will be there. So each team need to build their own block. Okay, so all the blocks need to get at a time. Okay, we need to clear all the things, the coverage or assertion. So you can imagine how quickly they need to reach to the market. Okay, so time also demandable, right? And moreover, verification. SOC level verification is very complex thing. It is not like a IP level or small block level. SOC means both the CCD, like core and normal input output. All the blocks will be involved, right? So there will be connection with all blocks. Okay, but we won't verify in the like a low level, because IP verification means very low level. Their signals we won't take at SOC level. Whatever the top signals are there, based on the top signals only we will verify. Okay, so that is the difference. Next, what are the different challenges in the SOC? So these are the different challenges in the SOC, like architecture strategy. Okay, we need to make architecture strategy. So how architecture, what type of processor we need to design SOC for in the real time. Okay, so what kind of bus implementation, what type of control signal implementation, all these things we need to make a strategy. So what is the previous processor, what challenges we have met, and what are the features we have added. Any features are not good in the market, so that we can remove those things which are not highlighted or which are not succeeded in the market. And next, design for strategy, design for test. What is the design for test? Mostly physical design side. Okay, at the physical design side, physical defects. Okay, we need to check for the fault, socket faults. We need to check for next version. We need to make more advantage. Okay, so physical detects which are nothing but faults, and mainly design for test means checking for the fault only. And validation strategy, is nothing but mainly S4C have two major issues. Okay, it mainly involved in the two major issues. One is the we need to verify IP core. Okay, IP cores. Second one is we need to verify the integration of the system. Okay, so these are the two strategies we need to check. And synthesis backend strategy. Synthesis backend strategy is nothing but there will be so many physical effects. Okay, we need to consider while doing the S4C synthesis. We need to make strategy that there, like effects of crosstalk, 3D noise, antenna effects, and EMI effects. Okay, these all will be involved. Noise will be involved mostly. So in order to tackle these issues, mainly chip planning, power planning, or DFT planning, area budgeting, clock planning, timing. So all these are required in the early stage of design. So mainly synthesis backend strategy also important, but we won't do everything. Whatever the team, every team have their own strategies. They will look into it. Okay, so only one person or only one team will not handle all these things. Okay, and integration strategy, integration team also will be there, CDP team integration. So whatever assembling, okay, so it is nothing but just to go on smooth strategy. Okay, they will put some strategies which can move very smooth. Okay, and on chip isolation, is nothing but like grounding effects. Okay, we'll get the grounding effects, guarding, shielding on chip, and decoupling effects. Okay, so these are the things which we check in the on chip isolation. So mainly these are the challenges which we face in the S4C architecture, S4C design challenge. And so these are the various varieties of the system on chip. Okay, so NVIDIA and Intel, Qualcomm, AMD Ryzen, NVIDIA Tegra, Samsung, Texas. Okay, so tomorrow we'll discuss detail on these S4Cs and what are the different ARM S4C and AMD S4C. Okay. Yesterday's session we have discussed on introduction to the ASIC and FPGA and what is meant by S4C architecture, right? So can anyone tell me what is the difference between FPGA and S4C? What is the difference between FPGA and S4C? Yeah, am I audible? Please make the session interactive so that we can discuss the things. Yesterday we have discussed on the ASIC and ASIC design. In ASIC design, there will be full custom design and semi-custom design. We have discussed brief on that. So what is the difference between standard cell based and gate array? And what are different programmable ASIC? Okay, so PAL, PLA, GAL, CPLD, FPGA, all these things we have discussed. So finally, system on chip. What is meant by system on chip? And what are the different blocks involved in it? Okay, so how system on chip will look like? Okay, example. So what are the advantages of SOC and disadvantages, and what are the challenges? Okay, challenges of SOC in the industry. What are the different strategies we need to make? And different SOCs, like whatever we have seen up to now, different product company from Intel or Qualcomm or AMD, NVIDIA, graphic processors. We are seeing all these things, right? So these are different SOCs. And today we are going to start with the difference between monolithic and multi-chiplet. Okay, so what is the difference? Monolithic and multi-chiplet, both are SOCs only. Okay, if you see the past system on chip x86 from Intel, okay, they have used x86 processors. From x86, ARM introduced some other processors like based on the CISC and RISC architecture. Okay, so AMD Ryzen has introduced the multi-chiplet from the Intel, where Intel used the monolithic. Okay, monolithic is nothing but all the circuit will be integrated on a single chip or a single die. So from that, AMD introduced the chiplet design. Chiplet in the sense both cores and IO devices will be separate. There will be number of dies. Okay, a chip has divided into number of dies, and each die have some CCX configuration and IOD configuration. Okay, we will discuss all those things now today's session. Okay, how AMD chiplets are working, the configuration. So whatever we are seeing the configuration, same thing nowadays, whatever we are doing the project, okay, same things we are going to implement there. Okay, overall SOC. So today we'll see just block diagram of overall architecture, and next session we can go through internal block diagram of the SOC architecture. What are the different blocks? Suppose if you see multi-chiplet means it have the CCX configuration and IOD configuration. In CCX there will be multiple CCD. Right. So what is meant by CCD? How many cores involved in that? What are the caches? What are the threads? What is the difference between thread and the cache and core? Okay, so we are going to discuss all these things today and in the next session. Okay, so that introduction with the SOC will be completed in first week. Okay, so if you have any doubts in the session, you can ask, you can clear your doubts in session itself. And tomorrow morning, I will provide you the reference material for yesterday's session and today's session. Okay, so coming to the difference between monolithic and multi-chiplet. So whoever knows some any points, you can share here. So what is the difference? So as I told, like monolithic is nothing but it is one integrated, all are integrated circuits only, or all are ICs only. Okay, but different configuration is different. Okay, so monolithic is a integrated circuit, and all the components are placed on a single die. Okay, you know the single die means how actual architecture, if you see actual processors, there will be a package in the sense internal there will be one die, by using the here there will be pins, IC pins. If you see in your laboratory and all, the die will be connected to the package with the pins like this. Okay, so here there is a single die. Okay, in this single die, there will be processor, number of cores, number of caches, okay, and data fabric, control fabric, and multimedia hub, everything. Okay, whatever IO devices will be there, whatever memory blocks will be there, everything will be connected in a single die. Okay, so that is nothing but a monolithic chip, integrated circuit. Okay, so like your motherboard. Okay, if you see olden days, the components where we have large devices. Okay, so there will be resistors, capacitors. One side there will be the processor and RAM modules. Okay, RAM ROM modules, and there will be some small capacitors and resistors. Here sides there will be ports. Okay, so all these are one integrated package, right? So that is nothing but monolithic model. So all different circuits are involved or integrated in a single chip. Everyone understood? So what are the advantages of monolithic? These are hybrid chips. Okay, so very simple to process. Okay, and using the single die, right? So it is easy to manufacture. Okay, so that is monolithic. Did you all understood? And it has low power consumption and poor isolation. Okay, compared to the multi chiplet, it have the poor isolation and lack of flexibility and a small range of values of passive components. Okay, so these are the disadvantages. And mainly another disadvantage is both the digital blocks and the analog blocks will be connected here only. Okay, digital blocks, whether it is a processor or it is a memory block or it is an NBIO or SBIO, whatever. And analog components or capacitors or diodes, resistors, everything will be there on the motherboard, right? Both the analog and digital, whenever it is connected, so noise is coupled between the blocks, right? So that is one of the disadvantage with the monolithic. So we'll get the extra guards on the ICs and heating effects will be there, more power heating effects, and there will be variations in the voltage and the current. So these will be common disadvantage in the monolithic. Okay, everyone understood?
Yes, ma'am.
Okay, so what will be the applications of monolithic? What are the applications of monolithic processors? Already, I think you got the point. See, every olden days, wherever we have used the computers and all, they're all are monolithic only. Okay, the motherboards and all monolithic based only. So those are the examples for the monolithic integrated circuits. Okay, so everyone got the point. Please, please be interactive. Okay, next one. What is mean by multi-chiplet? What is mean by multi-chiplet? Multi-chiplet is nothing but uh, there will be number of dice. Okay, on the same package there will be number of dice. Okay, so based on the configuration, whatever the specification, we will divide. Okay, based on the CCX or IOD, number of cores, based on the number of cores and number of dice, we will make the partition. Okay, suppose here there is a package. This is the package. In the package, there will be multiple dice. Die 1, die 2. In die 1, there will be number of cores, number of related to IO and CCX related cores, and another IOD configuration, or all or CCX configuration. So we are just making a large piece of integrated circuit into small chiplets. Okay, so before we have seen one monolithic, this is the package, and one die. In that die, all the things, processors or cores or data or control memory modules, everything are integrated on a single die. But here we are separating into number of dies. Okay, so in each dice there will be core, processor separately, and IO devices separately. So that is the process. So what happens if we take separate dice in the multi-chiplet or in the monolithic? What is the advantage if we move to the multi-chiplet?
Hello.
Yes.
What is CCX configuration?
CCX
Means what is the what is the
CCX
use of that configuration?
CCX configuration is nothing but core configuration. Okay, so CCX is nothing but core related. In that we'll have the core and cache memories. Okay.
Okay.
Yeah. So what is the full form of CCX?
I don't know. That's why I'm asking.
Yeah. Core complex. Okay. We can call it as a CPU complex or core complex. Nothing but it stores, it have the number of cores and number of cache memories. So what is mean by core? What is mean by core?
Core means
Yeah,
it comes under CPU, means all CPU processing unit under CCX.
Okay. So core is nothing but it is also a processor, but name we tell as a core. Okay, nothing but processors.
Okay.
Yeah. So in CCX, what happens? We'll divide into number of cores. Okay. So number of cores and number of IOD devices. Then what will be the advantage? Suppose here there is a, I will give you small example. So here there is a monolithic, and this is the multi chiplet. So in monolithic, suppose one or the die is divided into number of blocks. Okay, these are the number of blocks, and here in multi-chiplet there will be so many dice. Okay, 2-3 dice. In each dice there will be so many blocks, right, separately. So whatever this entire structure is there, so in each die it will have the same structure. So there will be n more number of blocks. Okay, so if any error is detected or any defects are there, suppose in multi-chiplet and the monolithic, suppose some errors are there in this, here some detections are there, here and here some defects are there, and here also there are some defects. Okay, in same chip, here there are some defects, and here there are some defect, 4 defects, and total number of blocks. Okay, what are the total number of blocks here? 1, 2, 3, 4. 5, 6, 7, 8. 20 number of blocks are there. Then what will be the yield? 4 detections by 20. Okay, 4 detections by 20. Then what will be the percentage? 4 by 20. Are you understanding? And here maybe the dice are more, right? Complex. So here number of detects maybe some 40 and number of blocks will be 100, then 40 by 100. So the percentage will be here higher percentage and here lower percentage. Okay, so yield will be high. Okay, so that whenever we have defects, the entire chip is not affecting. Okay, so it is easy to detect the defects and to go for debugging. Okay, so that is what. And next thing, what are some other advantages? If you discuss something, we can discuss more. Otherwise, I can tell the session and I can leave.
Ma'am, would you explain one more about multi-chiplet? Means yields 40 by 100 means here yields is more means what is the advantage? For debugging, it will be easy or else any advantage is there?
Yields or high means we have see detects will be more. If detects will be more means in entire suppose wait, I will show you so that you can understand. See, suppose here this is the monolithic. Monolithic means some suppose only one block is there, but in multi-chiplet there are 2 dice. Okay, 1 die and 2 dice. Suppose some defect is there in this die. So what happened? That defect will be affected to entire die. But here in the same place, here one defect is there. So is it affecting entire package?
No.
No, there are 2 dice. So this die is good and this die is defective. So that we can check only with this die. We don't need to check all entire chip. Okay, that's what yield percentage is high here. And whereas monolithic yield percentage is low. So that the overall chip defect will be high and we cannot capture it easily.
Okay.
Okay, and as I said, divided into number of dice. We'll discuss that thing. And the main goal of the chiplet design is to reduce the manufacturing cost. Okay, so it have multiple chiplets, right? So no need to put all the things in the single die. If you put all the things in the single die, what happens? It very bulk in size. Okay, transistor size is very bulk and all the components on single chip means every component occupies more space on a package, right? So that's why the cost will be more. But whereas a chiplet means in the single die we are making all components in a small chiplets. For core it is a separate, for IO devices it is separate dice. That's why the manufacturing cost is less, and it reduces the number of types of chips, and it is made safety to and quickly to the market. Okay, so no need to depend all the things on the package. So whenever one small chiplet is completed, it doesn't depend on other, right? So that's why it is time to market is fast, and it is easy to debug also. Okay, easy to debug means every block is a separate. Okay, I will show you how it look like. So debugging also easy because separate configurations will be there for both core and IOD. No need to mix all the things and no need to debug entire at SOC level. Okay, so that is difference. And here each package will be divided into the dice. So each dice have number of cores and threads. Okay, and AMD has introduced the CCX configuration in the multi-chiplet, and the die consists of separate CCD and the IOD blocks. So we'll see what is that.
Madam,
Yes.
what is meant by thread here?
What?
Thread. Just now you told about thread.
Yes, we'll discuss. Right. Next slide we can discuss. Okay. So as I told, see, here is the some difference. If you see for monolithic and the chiplet, it delivers higher yields. Higher yields means as I told that suppose if any defect occurs, entire die will be need to debug. But here at the same place, if any defect occur, only this die we need to check. Remaining all three are safe. Okay, so that is a higher higher yield. So how you can calculate higher yield means all total blocks by defects by total blocks. Here also number of defects by total blocks. Okay, and these are the somewhat differences, and more performance and lower cost as we discussed, because no need to put all the things in the same die, and flexibility. Okay, so next how if there are dies here, how they are connected each other. So here is the one die and second die, third, fourth. So here these are the interconnections. So how these interconnections? Every company has its own interconnections, like SSB DCI, okay, DDR SSB, like data rate. Okay, so based on the data rate, double data rate or single data rate, we can transmit the data. Okay, so that is how we will connect the die to die. So if you go in depth of SOC architecture, we'll see how there will be sub blocks also while connecting. So which block will be connected, like a SMN network, system management network, how the system management network will be work while connecting all the things. Okay, so these are we are going to do. And next, these are the different monolithic and multi-chiplet compared to the design cost. So multi-chiplet has high cost because it is a 7 nanometer and nearly $2,200 millions cost. Okay, and whereas chiplet is a less cost because of we are dividing partitioning entire chip, so that power will be less. Okay, and next, design time, longest design cycle. Okay, so for monolithic, longest design cycle, because every block need to connect with all blocks. Okay, but whereas in a chiplet it is not like that. For suppose you are doing for core. Okay, how you will design the core? Core is nothing but processor. How we will design the processor? Suppose RISC processor is there. Okay, mostly ARM company use the RISC processor, or Intel company use some other x86 processors. So every company has its own processor and own instruction set. Whatever we are seeing our like at the study time, those instruction sets will be different, and in the company whatever they are using, those instruction set will be different, somewhat complex, more complex. Okay, so how we will design the core based on
Which
the
instruction set we will be using for RISC processor, ma'am?
Sorry,
Which instruction set we will be using for RISC processor?
we are using ISA. So
What is ISA,
type
ma'am?
of ISA means instruction set architecture. It have its own instructions like I type instructions, R type instruction, register type, jump type, and branch type instructions are there, right? So those instruction set we are using for RISC-V. And mainly that doesn't depends upon the RISC-V instructions. Also instructions mostly common, but if you go to industry, somewhat more complex things will be involved, not like simple instructions like immediate instruction, register instruction, not very simple, like a jump type instructions. These type of complex instructions will be involved because we are doing the project level, right? So mainly the processor architecture, it will be dependent on not on instruction, based on the architecture. Suppose if you say RISC-V has some architecture and CISC has some architecture. Okay, RISC-V means mainly depend on the pipeline, number of stages like fetching, decoding, executing, and memory. Okay, so based on the pipeline, we will write the instructions. Okay, there will be instruct architecture. Suppose how the RISC architecture will be look like. First, we need to fetch the data from instruction. Okay, so it will be byte addressing for the RISC-V, right? So it will increment for +4. So after fetching the instruction, based on the instruction, it will go to the execution. Okay, so in the execution, what will happen? How it will execute the data? Suppose the instruction is add register 1. Register 1 may have some data like 4C. Add reg 4C comma 2. Okay, so that it will add the from the source register and destination register. It will add the data and it will store in the register. Okay, so this instruction will be executed here. There will be internal ALUs. Okay, so from that it will send to the decoder. Why decoder? Because this is the instruction what we are telling to do to the processor, but internal processor will not understand the instruction, right? The internal processor can understand only in the binary. So this instruction will be decoded here. So decoder is nothing but actual information. It will transmit to the into the binary. Okay, so whatever we got the data here in the binary based on the instruction, that it will be understood by the processor. Okay, so it will be depend upon the processor architecture, which type we are using. Did you understood? So whatever, suppose here it is sending the data in binary 100 or something 1000 like that. Okay, so, this is some binary information. So how we will decode that binary information? Not decode. How we will debug that binary information for processors? Suppose here this is the CCX for core. And here there is a IOD. IOD in the sense normal input output blocks. Okay. Suppose here input output block means we'll take one multiplexer. Okay, for simple understanding, multiplexer or any register will take. Okay. So how we will design this multiplexer? How we will design this multiplexer? How we are designing? Nothing but Verilog program, right? By using the Verilog, we are designing the multiplexer, and one schematic will generate one schematic. Like that, if you go for architecture level, there will be various blocks involved, memory block or graphic processor block or some NBIO or SBIO or multimedia hub, different blocks involved. So everything we are writing Verilog program and generating the RTL schematic. So here we are generating RTL schematic, but for processor, we are writing the instruction and we are generating the binary data. Okay, so both we need to verify now in the SOC level or in IP level also, we need to verify. So by using a system Verilog or UVM, we are verifying these things. Okay, whatever we are generating the schematic diagram using the Verilog HDL, we are doing verification with system Verilog or UVM. But here all the information is binary, right? Is system Verilog accept binary data? Mostly system Verilog means it is similar to the Verilog only. It have the registers, wires, and all related to the timing, clocks, everything related to the Verilog. But whereas here processor means all are it is generating in binary format. So here we cannot do the verification using system Verilog or UVM or any verification HVL or HDL methodologies. Okay, so here we are using the C based. So that's why
Ma'am, one doubt.
level. Yes, tell.
In system Verilog, we are using binary data also, no? Verilog, system Verilog also.
In system Verilog we use binary data, but it cannot understand. It cannot convert. We cannot write the test cases for binary logically. So many things it will not allow.
Okay.
Yeah, mainly it is preferred for the HDL only.
Okay.
Okay, so yeah, that's why here we are writing in terms of C language, because C language is very eco-friendly to the binary, right? So it is easy to generate all test functionality for the binary. That's why in SOC level we use the C or C++ test cases. Okay. So any other doubts?
No, ma'am.
But actually, we're declaring the binary in the Verilog and system Verilog, right? Like tick B and all.
Sorry.
We're declaring the binary values, and while doing the code
Yeah,
coverage and all,
we are declaring the binary values in SOC, sorry, in system Verilog, but that is only for writing the test case. Okay, while doing the randomization and all, we are just allowing for binary data to generate the binary data. Okay, but
Okay.
internal language itself, it doesn't, it can't take the binary.
Okay.
Okay.
Can you explain with the examples, like if possible,
For what?
like how to give the binary and all? Like what is the difference between
Yeah,
SV and
we
C?
explain while discussing projects, I will explain clearly. Okay, so
Okay.
in this we have added the RISC-V also. So while discussing
Okay.
RISC-V SOC architecture, we'll discuss everything this. Okay.
Okay.
Yeah. Any other doubts, Maunika?
Ma'am.
Okay. Can you all
Ma'am,
please?
would you explain pipeline structure in SOC? Means it's a five-stage pipeline. How it happened?
Okay, okay. Can you all please join for the next session quickly? It is a 40-minute time limit. Next thing is one of you asked, Monica asked for pipeline, right? So pipeline will discuss more detail in the RISC-V, but I will give you overall idea. So pipeline is nothing but, what is mean by pipeline?
It will happen in parallel process, means any address and data phase is there, means in first cycle address, second stage both address and data will do parallel same cycle in second.
Okay, so then what is the advantage of pipeline?
Time consuming will be less compared to normal things.
So every processor or every program or any protocol, wherever there will be some kind of process. Okay, so fetching the instruction, executing the instruction, decoding the instruction, and again sending the instruction to the memory. Okay, so every time we will follow these steps. Okay, and write back stage also will be there for memory, right? So while doing these 5 steps, if we don't do in pipeline manner, it will take more time. But in pipeline means while suppose if you take risk only, so while fetching the instruction, how it will fetch the instruction? How
I
it will
don't know,
fetch
ma'am.
the instruction? So there will be one
Based on instructions.
and yeah. So in the fetching, first is the fetching stage. Okay, in the fetching stage, based on the memory and based on the address, okay, already we will give the byte addressing for the risk. Okay, so byte addressing means every address will be incremented for +4. Suppose it is started with the 20 address. Again, next address will be 24, next 28, next 2C, like that. Okay, so this will be the address. So first it will fetch the instruction from the address, and there will be some other blocks also involved. So from these there will be instructions, whatever we are writing the program, that instruction it will fetch into the memory, and after that it will send to the decode stage. Okay, what happens in the decode stage? There will be some registers in the decode stage. So whatever we have written the instruction, it will decode the into machine understandable language, internal processor understandable language. Okay, so that processor understandable language is nothing but what is the source, what is the destination, and what is the instruction. Okay, that instruction will be converted. Decode is nothing but here there will be some ALU. Okay, ALU in the sense, suppose if you are sending the instruction as a arithmetic, so that it will decode that instruction as a add to ALU block diagram. If you are sending some other logical like XOR or AND, that logical data will be converted using the ALU. Okay, so that happens in the decode. Once decode completed, that instruction will be sent to the execute stage. In the execute stage, it will execute the instructions, and then it will send to the memory access. Okay, memory access and write back stage. Write back stage is nothing but again writing to the same registers. So this is how pipeline. So pipeline is nothing but, suppose while fetching the data is there, then next it will go to the decode. While decoding the data, again next instruction is fetch. Okay, and first instruction is in execute stage, then second instruction will come to decode stage, and third instruction will come to fetch stage. Okay, and while doing these executions, okay, parallel pipeline execution, in risk processor we have some bypass stall conditions are there. Okay, because to avoid the speed, okay, if unused cases will be there, right? Sometimes so to avoid that, there will be stall conditions, bypass conditions. So those things we'll discuss briefly whenever we discuss those sessions. Okay,
Thank you, ma'am.
this is what the processor, how we will write internal hardware. Okay, this is all related to the hardware. Once hardware completed, once design completed, then we do the verification. Okay. And
Is there
next,
something like 3-stage pipeline and 5-stage pipeline?
yes, 3-stage pipeline also like same only. And 5-stage pipeline, 6-stage pipeline also same. But internal, suppose if you see 6-stage pipeline, 5-stage and 6-stage, 6th stage both are same only. But registers will be added internally, so that will be difference. 3-stage means just fetching, executing, and fetching, decoding, and executing like that.
Can you repeat, ma'am?
Yeah, we have different stages of pipelining, like 3-stage, 5-stage, 6-stage. Suppose now we have seen 5-stage, right? Fetching, decoding, executing. Next, memory access. Next, write back stage. So that is one advantage. If we have write back stage, we can write to the memory or any existing register. Or if you go for 3-stage pipeline, we have only fetching, decoding, and execution. No memory write back stage. So those are somewhat limitations for 3-stage. If you go for 6-stage, some other registers will be added. Okay, in last stage. So that will be advantage. While writing complex instructions, so you can store some data to some registers, and whatever unused data is there, you can store to the same register like that. Okay, any other doubts? So coming to the performance, so monolithic have good highest performance, and but some functions might not scale, so would use a large design rule for the portion of the chip, and it leads to the inefficient use of resources. Whereas a chiplet, it have good performance and can use most appropriate process for the function needed in the chiplet. So compared to the power is less in the chiplet only, and time to market, chiplet is quicker compared to monolithic, and product size, both are small. Okay. Monolithic is compared to the chiplet, monolithic is somewhat complex. Okay. And next one, AMD multi-chiplet. So what is AMD multi-chiplet compared to the Intel monolithic? What is meant by multi-chiplet? So if you see here, this is one package. Okay, here this is entire package we can call. So in the package, two dies are there. Okay, die 0 and die 1. So die 0 and die 1 are connected with the fabric. Okay, as I told, SSB DCI, like that. And here some of the cores are there: CCX0, CCX1, CCX2, CCX3. Okay, this is one version of a multi-chiplet. Okay, so now suppose here just a second. Okay. So what is the difference between core? Here there are 4 number of cores. What happens if there are more number of cores? What is the advantage if there are more number of cores?
Error detection is possible.
Error detection is possible. Okay. Any other answers? No. Okay, more number of cores in the sense we can do multiple task. Okay, So at the same time, it can involve the in multiple tasks. Okay, so multiple core processor, if there are n number of more number of core, mean the speed will be high. So more high core count is equal to high speed. We can tell like that. Okay, so nothing but it enhance the performance. Okay, whenever there are multiple more number of cores, it enhance the performance and it will reduce the power consumption. Okay, so nothing but simultaneously it will process the multiple task and parallel processing, multi-threading, we can call as a multi-threading from Intel, we can call. So that will be hyper-threading and multi-threading. So what is the difference between what is mean by hyper-threading? Okay. So next, if you see here, this is third generation AMD Ryzen with the 2x CCD plus IOD configuration. So in one CCD, there are two CCX with 4 core 8T and 16 MB L3 cache. So what is meant by 4C8T? 4 core 8 thread. So what is the difference? Core is nothing but it is one part of the processor. It will perform the calculations, instructions, and all. So thread is nothing but it is also a type of core, but there will be sequence of instructions that can executed independently by the processor. Okay, so whenever processor have multi cores, it can perform multiple calculations, instructions, everything simultaneously, but multiple threads can execute multiple sequence of instructions based on the core. Okay, so nothing but more cores is not more cores will be given better performance that require the low processing power. Okay, so whereas a thread is also required for the multiple tasking. Suppose you have 4 number of cores and 8T. Okay, so whenever you want to put multiple number of tasks, okay, when you are doing some video game and all, when you are putting multiple number of tasks, then multiple thread is uh, uh, we need to use more number of thread. Okay, have you understood what I told?
Ma'am, what is CCD here? Above.
CCD is nothing but core complex die. Okay.
Would you explain once this 4C 80 16 MB
Yeah.
L3 this one?
I will explain you. So can you tell me what is the difference of? That's what I'm asking. Okay. So whatever if you observe everywhere will take 4C 8T. Okay, 1:2 ratio. Suppose if you take 1:1 ratio, what will happen? That means 4 core 4 thread. 4 core 4 thread.
No idea, ma'am.
No idea. Okay, see, I will tell you some other small example. Suppose the core, the difference between core and the thread. Okay, core is nothing but simple computing with the independent. It is a component which done simple computing, which is independent to the CPU. Okay, so it will read and execute the program instructions. Whereas a thread is nothing but larger programs will be divided into the threads, small sections, so that processor can execute them, and simultaneously to get faster execution, it will execute, okay, which is divided into small threads. Suppose we have hyper threading also. What is the hyper threading? It means CPU has, if suppose CPU has 2 cores or 4 threads, okay, simultaneously through hyper threading, one physical core can only run and one thread at a time. One core, one thread will be run at a time. But using hyper threading, CPU explodes the ideal stages in pipeline to process another thread. Okay, so that what happens? Simultaneously, we can run the more instructions. Have you understood?
Yes, ma'am.
Okay. So others, what about others? Okay, I will tell you another example. Suppose you can consider like you have some data in your hand, okay, and just consider one piece of bowl, okay, or just take one pet, any dog or something, okay. Suppose dog is your core and your hand is thread, or its hand is thread, okay. So whatever the process is done by CPU is nothing but eating food by dog, okay. So that is nothing but CPU. Now dog is the CPU, or any pet is the CPU. What is that main purpose? It is eating food. Food is the main purpose because it is doing some task there. Okay, so I'm considering as a CPU. Eating food is nothing but CPU. So if you have multiple mouth, it can eat lot, okay. Within some time it can eat more, right? But it would be, what happens, there will be some limitation there. By your suppose you have only 2 hands to put multiple mouth, so there will be bottleneck there, right? So it will speed would be slow, okay. Even you put so much food, it can't able to eat, okay. So otherwise, if you have multiple hands but only one mouth is there, or one dog is there, so what is the problem? If you have multiple hands, only one dog is there, it cannot eat all the food, right? Even if you have lot of food, it cannot eat. There also, there will be the restriction. So what we need to say here, to complete the balance between the thread and the core, okay, one mouth, one hand is enough, or one mouth, 2 hand is enough, okay. But multiple things are not allowed, right? So synchronization is missing. So that's why to complete the balance between thread and the core, you can to get the better efficiency, we need to take in 1:2 ratio. One core, 2 thread. Okay, for doing one instruction, 2 threads can be used. If more number of threads is there, the core cannot take as a challenge. Okay, it may not bear. Did you understood?
Yes, ma'am.
So early,
Yes, ma'am.
whatever we have used in olden days, there will be only one core, 1 or 2 core. But nowadays, cores are improving, right? For every generation, if you go for i5, i7, it's nothing but number of cores are increasing. So when number of cores are increasing, multi-threading, these concepts, hyper-threading will be increasing. More number of tasks can be done. More number of tasks, mostly using for video purpose or gaming purpose, video editing purpose nowadays, right? So that is the advantage if more number of cores and caches increase. Okay. Okay, now suppose my question, I have both 4 cores and 4 threads. Then what will happen? 4 core, 4 thread. It is just introduction session, just to know the basics of SOC. This is not actual course. Okay. So we need to know, right? What is the chip, what is meant by core, what is meant by thread before going to SOC, because all these are included in the SOC, right? That's why. So what happens if there are 4 core and 4 threads? Will it do better task and better power handle mechanism and multiple tasks at once? Okay, just work on that. What happens if we take core and thread in 1:1 ratio and 1:2 ratio? Okay, what is the difference? Okay. Everyone clear up to here? Everyone understood? Okay, next, what is the difference between CCD and IOD? CCD is the core complex die. IOD is the input output die. So what is the difference? You can observe here clearly. These are the very most asked interview questions in the SOC verification. Mainly you need to introduce about multi-chiplet. Okay, so what type of, if they ask the question, what type of SOC you have worked? So I have worked on the multi-chiplet model SOC. It consists of 2 different dies. One is for CCD configuration, another die is for IOD configuration. In CCD is nothing but core complex die. It consists of core related. So you can tell some of the core, like whatever AMD cores are there or Intel cores are there. I will give you the reference material so that you can go through the reference materials. You will get the idea which type of cores are used by different companies. Okay, so you can tell in CCD the the different blocks are nothing but cache memory and cores. Different cores are available. And coming to IOD, data fabric, control fabric, and memory controllers, and multimedia hub, and North Bridge IO or South Bridge IO, or various blocks. There are so many blocks involved in the IOD. Nothing but those are input output. Here, what is the difference means? For IO and for core, we are doing separately. Whereas in monolithic, all are in same die, right? But here for core, different die, IOD different die. That is only difference in present processors. Okay, everyone got clarity?